Alright guys, welcome to 9.2 Polar Equations and Graphs. We're going to graph some more equations in polar. So we're going to learn how to do that with a graphing utility. We're going to look at some symmetry, and we're going to plot some points. It's kind of what the road ahead looks like for 9.2. So just to remind you guys that a rectangular grid is the typical graph that we know. But with the polar grid, we have, various angles that go around circles. So these are like concentric circles that are going out, and each concentric circle is a unit of 1. So definition 1 says an equation whose variables are polar coordinates is called a polar equation. We've talked about that. The graph of a polar equation consists of all points whose polar coordinates satisfy the equation. Okay, so let's get into this, guys. So objective 1 is let's identify and graph polar equations by converting to rectangular. So first off, they give us a nice easy one. They say, okay, what if r is equal to 3? Well, if r is equal to 3, r, remember, stands for the radius, the length of the radius. So if r is 3, and that's all we know, what that's going to look like is it's going to look like a circle that has a radius of 3. Okay, so it looks something like that. And the center is going to be at 0, 0. Okay, so that's all it is. If we were to convert this to rectangular, we know that we could square both sides, right? So we'd get r squared is equal to 3 squared. So then we know that r squared is equal to x squared plus y squared, so we get x squared plus y squared equals 9. And remember that since x squared plus y squared equals r squared, that 9 is the equivalent of r squared, okay, which in this case was 3. So now this looks like the equation of a circle, center at 0, 0, radius of 3. Okay, so that's example 1. Example 2 says now identify and graph a polar equation that looks like a line. Okay, so notice here they gave us a theta of 3 pi over 4. Okay, so the same thing, we're gonna try to convert this to rectangular. If I'm going to convert this to rectangular, one of the easiest things to do is to take the tangent trig function, because we know that that gives us an x and a y, and that's what we need, is an x and a y. So I could take the tangent of both sides. I could say tangent of theta is equal to the tangent of 3 pi over 4. And if I do this, I know that the tangent of theta is equivalent to y over x, right? Tangent of theta is equal to y over x. And the tangent of 3 pi over 4, that's 3/4 pi, which is over in this quadrant. We know that that is a slope of -1, therefore that's -1. Now if you didn't know that, you could plug it in your calculator, you get a -1. Okay, so if we solve this for y, we get y is equal to, multiply both sides by x here, we get -x. Okay, so the line y equals -x is what we would graph here for that given theta, which looks like this blue line that we see here, y equals -x. Okay, example 3, we're going to identify and graph a polar equation that's a horizontal line. Okay, so we have r sine of theta is equal to 3. Remember that r sine of theta, you guys, is, so if we go back to like our original, if we just were on a unit circle and we had this triangle, if we know that this is theta, we know that this is some radius r on the unit circle. Well, on a unit circle it would be 1, but let's just, assume that we're on a circle. And then we know for sine is opposite, or the y value, right? So sine of theta is equal to y over r. So we know that y is equal to r sine of theta. That's the proof for this. So r sine of theta is equal to y, therefore I can replace that with y. So this is y is equal to 3, which I can graph as a line, y equals 3. Okay, so that's the first part of the lesson. Second part of the lesson, objective 2, we're going to graph polar equations using a graphing utility. Now what I recommend you do, you can do this on Desmos. These are the graphing stipulations that you need for your TI. Okay, so you're going to change your mode in your view window when you go to graph to polar mode. And then you got to set your X min, max, and X scale so that what what you're viewing is within the parameters of the graph. And make sure that when you do this, you're putting this in terms of R and theta. So you're going to solve for R, and you're going to have a theta in there as well. And then there's this thing called theta step. So when you go to set your viewing window, you can set one of your options to theta step, and that'll help you with your view. Since your graphing calculator is used to an X and a Y, this is just a different setting that is available to you. So go ahead and I would play with this, try it out. You can also go to Desmos and then choose the polar function, and it'll pull up a polar graph, which is actually really fun to play with. So example 4 says we're going to graph a polar equation using a graphing utility. So they want you to graph r sine of theta is equal to 1. So what they want you to do is they want you to solve for r. This is the same thing as r equals 1 over sine of theta. And again, you can go on Desmos and do this. If you do this one, it's not going to be very exciting, but some of the ones to come will be exciting. This one, r equals 1 over sine of theta, is just going to simplify to this line that's here. Okay, so you have a line, just a horizontal line. Kind of boring, really. So don't stress this too much, but I would just encourage you to solve for r and plug it into your graphing calculator and just get some practice doing that. Example 5 says identify and graph a polar equation that's a vertical line. So for this one, we have r cosine of theta is equal to -2. Remember that r cosine of theta is just x, right? So this is x equals -2, which is a vertical line that happens at x equals -2. So we got this, I got this guy right here. Okay, so just remembering the various identities. Again, so r cosine of theta is equal to x. R sine of theta we know is equal to y. We know that r squared is equal to x squared plus y squared. And we know that tangent of theta is equal to y over x, which is useful. All of those are useful in these polar conversions that we're doing. So let's keep cruising here. Theorem 1, which I think I gave you in your notes, says that if we have r sine of theta is equal to some value, we know that that's a horizontal line, and if we have r cosine of theta equal to some value, we know that that is a vertical line. Okay, so that's the big takeaway from that theorem. We have a couple more examples here, and then I'm going to stop this video, and then we'll pick up the second half of the lesson next time. So example 6, we are identifying and graphing a polar equation that is a circle. So it says identify and graph the equation r is equal to 4 sine of theta. So what we want to do is we want to transform this to rectangular, which means we want this to be in terms of x and y. So to get that in terms of x and y, one thing we can do is we can multiply both sides by r. If I multiply this side by r and this side by r, what I get is r squared is equal to 4r sine of theta. We know that r sine of theta is equal to y, so I can write this as 4y is equal to, and we know that r squared is equal to x squared plus y squared. Okay, so by multiplying both sides by r, it allowed me to get things out of r's and thetas and into y's and x's, which is the goal. I circled this here, but this was not done yet. What I need to do here is to complete the square, which they did for us here, but just a reminder, we're just going to move that y over. So we have x squared plus y squared minus 4y. Half of -4 is -2. -2 squared is +4 equals 0. Since I added 4 in on this side to complete the square, I must add 4 in on this side, right? So I'm left with x squared plus y minus 2 is what that would factor 2 squared, is equal to 4. This tells me that I have a circle that is of radius 2, because this is equal to r squared, right? Radius is 2, and the center is at 0, because that's what makes this one go to 0, and 2, because that's what makes this y term go to 0. So at 0, 2, we have a center, radius 2, which is what they show here. 0, 2 is the center, radius 2. Okay, there's another one here that's the cosine version of this thing, so I'm just going to do the same thing. I'm going to multiply both sides by r. I get r squared is equal to 2r cosine theta. So then I know that x squared plus y squared is equal to 2x. So then I'm going to move my x over. So I have x squared minus 2x plus y squared is equal to 0. And then complete the square, right? So half of negative 2 is negative 1. Negative 1 squared is 1. So you end up with this guy. So I know now that my circle is at center negative 1 comma 0 with a radius of 1. Okay. Interesting. Why do they have this at a... Oh, sorry, it is positive 1. Sorry, I misspoke. Positive 1 is what makes that go to 0. So we have positive 1, 0 with a radius of 1. Okay. The last little bit here, and I think we'll be done with this one, is simply this theorem where we have r equals 2a sine of theta. Whenever this is the case, we know that we're going to get a circle. It's going to have a radius of a. Okay. Center is going to be at 0a. And that is what happens when we convert that to rectangular. Okay, for the negative of that, we know that we'd have the exact same thing, except for we now have a center at negative a. And then if we have cosines, notice that the x value is what becomes the a now. So this is all just saying that every time you simplify these, this pattern is what arises. So don't worry about it too much, because if you can convert to rectangular, you don't need to know any of this. This is just kind of a shortcut. All right, guys, that's it for this time. We will finish this off and get into some really cool looking graphs. Let me just give you a sneak peek if this will load. So a cardioid, see how that looks like a heart? We're going to get into some of those. There's just some really cool, we don't get into any tangent functions, but tangent of theta, graphing in polar, is very interesting. But yeah, we'll talk more about that next time.